Hello, and welcome to part 3 of my talk on ambient obstruction solitons and homogeneous gradient box solitons. So if you've been with us in part 1, we talked about some general geometric flows. I defined what I meant by that, and also gave us kind of a basis of understanding about what geometric flows are and how we study them. In part 2, I looked specifically at the ambient obstruction tensor as our measure of curvature, and looked at the solitons and really more broadly the methodology that we used to find and study ambient obstruction solitons. Now, in the third and final part of my talk, I'm going to be talking about homogeneous gradient box solitons. So I'm going to start by defining the Bach tensor. So for general n, the explicit representation of our Bach tensor is given here, where this W sub ijk L is going to be the Weil tensor. And the Weil tensor is some combination of the Schouten tensor, Riemannian curvature tensor, and the Ricci tensor. It kind of combines all of these measures of curvature together in a nice way. And the Bach tensor is defined looking at different derivatives of that, essentially. Okay, so we have our explicit representation here for the Bach tensor, and this is for general n. Now, I have said in the previous parts of this talk that this part is going to focus on dimension 4. So let's do that. We're going to see why in just a second. When I focus on dimension 4, of course, my coefficients change a little bit. And you can see that this definition aligns with our definition for the ambient obstruction tensor. Okay, I said in part 2 that the Bach tensor is the ambient obstruction tensor for n equals 4. Okay. So the Bach tensor here is exactly the same as the ambient obstruction tensor in dimension 4. Those definitions align, though they might look different. Okay. Moreover, in dimension 4, we get a lot of nice properties that don't exist or don't apply to the Bach tensor outside of dimension 4. So it really makes sense to focus our attention and energy in dimension 4 for all of these reasons. So in dimension 4, the Bach tensor can be realized as the gradient of the Weil energy, which is defined here. Now, if you have watched part 2, maybe you recall that we looked at the ambient obstruction tensor as being the gradient of the Q energy relating to Branson's Q curvature. Now, it's worth noting that in dimension 4, the Weil energy and the Q energy are very much related. They're related up to like a constant. So when I look at the Bach tensor as the gradient of either, the definitions do in fact very much align. Okay, so the Bach tensor can be realized as this gradient, and for all of the same reasons that our ambient obstruction tensor was cool being the gradient of an energy, our Bach tensor is still cool. Okay, meaning that because the Bach tensor is the gradient of this energy, metrics G that are Bach flat are going to be critical points of our energy here. Okay. We know, again, broadly, critical points are something that's going to be interesting, that should be flagged, especially in this bigger search for a best metric. Maybe a metric that's a critical point of an energy would be a good thing to consider as a candidate. Okay, and we'll get more confirmation of that in just a second. Just like the ambient obstruction tensor, we said, well, what if we look at some of the properties? So some properties of the Bach tensor is trace-free, and that actually holds in any dimension for the Bach tensor, not just in dimension 4. But focusing myself into dimension 4 again, I see that the Bach tensor is divergence-free, and it's conformally nice. And I defined this in part 2. I won't bother redefining it again. It's got some conformal niceness. Okay. Most importantly, I think in the argument for why we want to talk about the Bach tensor in the first place is that the Bach tensor actually vanishes for Einstein metrics. It vanishes for self-dual metrics, and it vanishes for anti-self-dual metrics in dimension 4. These 3 types of metrics, Einstein, self-dual, and anti-self-dual, were already considered to be interesting metrics. They were already probably candidates in this whole search for a best metric kind of an argument. Okay, so the fact that the Bach tensor flags these, marks them as 0, means 2 things. A, the Bach tensor is able to mark interesting things, and B, that these are also going to be critical points of the vital energy and of the Q energy in dimension 4. Okay, so it points to these other objects as also being interesting as a consequence. Okay, and before I get into defining the flows, I want to mention that part of what led me to study the ambient obstruction tensor was studying the Bach tensor. So this talk, I've kind of given it in a very backwards direction of how I actually found things. I started by studying the Bach tensor and finding Bach solitons. It's very hands-on, as you'll see. And I wanted a generalization. And because a lot of these nice properties don't hold for the Bach tensor, I ended up looking to the ambient obstruction tensor as my sort of generalization because it maintained these nice properties. Okay, and then a general Q that just had these properties. Okay, so just to fill in some of the details of the story of how this work is done, I started with the Bach tensor for these reasons specifically. Okay. So moving on to discuss the Bach flow a little bit. So the Bach flow, in general, for a smooth metric H, the Bach flow is given on the left. And that's on a general manifold. We still have this other scalar curvature term to contend with. Bio and Hello will talk about its importance in kind of counteracting conformal invariance. And I don't want to deal with it in my research and in studying Bach solitons for the first time. So I'm going to restrict myself to the homogeneous case, or if I wanted to, I could look at the constant scalar curvature case. We're really, in some senses, using these kind of synonymously. Okay. But when I do that, when I look at the homogeneous case, I see that my Q, as I discussed in part 1, is just going to be given by my Bach tensor. I won't have to deal with this scalar curvature term in the homogeneous case because it goes to 0. And so my Q is just the Bach tensor, and I'm able to just plug that Bach tensor in when I'm looking at solitons. It's also worth noting that I'm going to be focusing my energy on just gradient solitons. So because no one has studied Bach solitons up to this point, I wanted to look again and focus my energy into a case that had some niceness. So the fact that the gradient solitons have this Hessian term, and that's a relatively familiar term, made it a nicer case to deal with. Okay, letting my screen catch up for a minute and moving on. One of the things that I showed ultimately is this classification theorem. Okay, and this classification theorem culminates a lot of work, and I will go through kind of how I found that and also go through a specific example, assuming that I still have time. I don't want this video to get too long. Okay, so the classification theorem is as follows. Any homogeneous gradient Bach soliton that is steady must be Bach flat. And the only non-Bach flat shrinking solitons are product metrics on R2 cross S2 and R2 cross H2. Okay, so the only shrinking solitons are going to be product metrics on these two specific manifolds. Worth noting, Ho already proved the second part. He finds examples of solitons on R2 cross S2 and R2 cross H2. What I've done is just kind of go back in, firm things up, generalize things a little bit, but they really are just lemmas to his work. Okay. Also, another thing that I've proven as an offshoot of this, we've talked about steady solitons, we've talked about shrinking solitons, but what about expanding solitons? I've actually found an example, or class of examples, of expanding homogeneous gradient Bach solitons on the manifold R cross S3. Now, we're seeing product metrics in here and product manifolds in here. Haven't talked about them at all. Where on earth did that come from? So let's talk about it. Now, I first took inspiration from this theorem of Peterson and Wiley. Will Wiley is, or was, my PhD advisor. And so him and Peter Peterson had this theorem from 2020, which was that if we let our manifold be a homogeneous manifold, and Q is going to be an invariant 2 tensor, which is divergence free. So if Q is divergence free, then we know that all of our solitons are going to be product metrics on some manifold of the form Rk cross n, and our potential function f is going to be a function on only the Euclidean term. Now, this turns out to be pretty important when we're splitting up manifolds. But the big idea here is, as it pertains to us, is that if I'm only looking at homogeneous manifolds, check, we're going to limit ourselves to that, and I'm dealing with a divergence-free tensor Q, which the Bach tensor is in dimension 4, then I know that all of my solitons look like product manifolds, and that my potential function is only acting on Rk. Okay, my potential function is only a function of Rk. So this notion of splitting up manifolds really informs our approach to analyzing and finding these homogeneous gradient Bach solitons. We're going to really take a hands-on approach, but a quick note before I do that. So we're going to consider a product manifold where we're going to let M, our manifold, be split into RA cross NB with appropriate metrics on either. Since the dimension of RA is A and the dimension of N is given by B, I'm just going to refer to this as an A by B manifold. So if I refer to a 2 by 2 manifold, that's going to be a manifold where it's R2 cross N2. Okay. All of my manifolds M are going to be 4 manifolds total. So A plus B should equal 4. Okay, that's a helpful note for me. Okay, so A plus B will equal 4 because the dimension of my manifold is 4. Right. Other thing to note, the Bach tensor of a product manifold is not the product of the Bach tensor. So it's not, the Ricci tensor does something nice where it splits nicely over products. However, the Bach tensor does not. For example, on a 1 by 3 manifold, the Bach tensor is given like this. On the first manifold, on my first manifold, that RA component, it would be given like this. On my 3 manifold, it would be given by this term. And that's not super nice to deal with. But it is more manageable actually than one might think. So we have definitions for Bach tensors on all of the cases that we need. So the approach that we're going to take is we're going to break things up, and I'm going to enumerate them as this. So I'm going to kind of look at how my manifold splits by looking at how many copies of R there are. So I'm going to first start by looking at manifolds that aren't split at all. It's just a 4 manifold, it's not a product manifold, and we see that there are going to be 3 examples. More on that in a minute. Then I'll look at what if there are 3 copies of R? What about 2 copies of R? And what about 1 copy of R? Okay, it's really important to note that Helliwell does begin this investigation of manifolds of this type R cross N3. And he begins it by looking at the case where N3 is a unimodular Lie group. Consequently, the only manifolds that I've been able to start investigating are of that type, where N3 is a unimodular Lie group. There's still more to be done. Though the classification I gave is complete, there's more investigation to be had in this specific area. Okay, so let's look at some of these results and see how they stack up. So I'm going to be looking at first my manifolds N4, and I see that I have 3 different manifolds. Because I'm only dealing with homogeneous manifolds, it was very easy to kind of split up my cases here. Where I have R4, S4, and H4 are my only 3 homogeneous 4 manifolds. In this second case, I didn't have to consider any specific types. But one thing I do want to point out here is the differentiation between manifolds like this. R4, R2 cross R2, and R cross R3, right? Per Peterson and Wiley's theorem, we have said that I only want my potential function to act on the Euclidean factor, right? So when I'm considering R4 as a whole manifold, as a whole 4 manifold, my potential function is able to act on all 4 variables there. However, if I'm considering something like R2 cross R2, my potential function is only acting on these first 2 copies of R, on X and Y. And likewise, with R cross R3, my potential function is only acting on a single X. Okay, so that is why I have distinguished between these cases in this way. And enumerating the cases in this way actually enabled me to find my result to show that of these first 3 types, everything is going to be Bach flat, or it's going to be a steady soliton, and the only 2 that are shrinking are these 2. And again, in this last case, I was able to find an expanding soliton here for S3, or R cross S3 with this potential function, but more on that in a minute. So the theorem that really does the work in this classification is this. For any homogeneous 3 manifold N3, I'm going to consider this product manifold. If I look at the, or I can say that the manifold is a Bach soliton if and only if the Bach tensor restricted to N3 is equal to -2 CGN. That is to say, the manifold is a soliton if and only if this ratio of Bach components to components of my metric are equal to -2C. They all need to be equal to one another. Okay. And in forcing this relationship to happen, we see that we eliminate a lot of cases. We eliminate things from possibly being metrics or possibly being solitons in this pretty expansive R cross N3 case. Okay. The proof of it is actually quite simple. So I know that my potential function is only a function on that first copy of R because my manifolds are of the form R cross N3. My second order derivative in the 0, 0 case is just, it's my second derivative. And since F was only acting on my Euclidean factor, that first factor of R, I know that all of my other partial derivatives are 0. What this means is that my Hessian, that matrix of second order partial derivatives, looks like this, because my 0, 0th term looks like that. And all of the other terms for various ij's are like this. My Bach tensor is going to look like this, as is my metric. And I know that I'm able to diagonalize these matrices. And again, talk more about this in the paper that's involved. Okay, so I get this wonderful system of diagonal matrices, and we can really just go component by component to link things up and see what needs to happen. So from this, we see that -1/2, doing it quickly here, with the B11 case, I see something like this. -1/2 B11 equals CG11, -1/2 B22 equals CG22. So B11 over G11 equals -2C, but so does B22 over G22. And again, obviously the same thing applies for B33, G33. So from this, I very quickly get that this string of equalities needs to hold, and I need to equal -2C. And so that's in the forward direction. And in the backward direction, it's actually quite similar. Before I do that, I'm going to do a quick corollary that will help with the backward direction. If a manifold of the form R cross N3 with this metric is non-Bach flat, then it's expanding. Okay, we know from here that these guys have to equal -2C. So moving on, if I have this equation, I'm able to say that if it is non-Bach flat, or I should start here, because the Bach tensor is trace free, I know that B00, B11, B22 plus B33 is equal to 0. I've just taken the trace of the matrix that represents the block tensor here. Subtracting B00 and dividing each one of these terms and multiplying by G11, G22, and G33, I very quickly see that I get negative B00 equals these guys, but each of these was equal to negative 2C. So consequently, I end up with B00 equals 2C times G11 plus G22 plus G33. Using the equations that I gave a few slides ago for 1/3 components and Cauchy-Schwarz theorem, I'm able to conclude that this forces B00, or that these two things force B00 to be negative or equal to 0. Since my metric is positive definite, that means that this term is positive. So how do I do this? This guy is less than or equal to 0. This term is strictly greater than 0. And these two things together combine to force negative 2C to be less than or equal to 0. Well, we know that C is equal to 0 if and only if B00 equals 0. And furthermore, if B00 is not 0, i.e. our metric is not Bach flat, then our soliton is expanding if C is less than 0. Okay, so we get this quick corollary. It has these kind of nice, very computational proofs. We get a second corollary that follows very quickly. Again, if C equals 0, then B00 equals 0 from the previous slide. And consequently, we're able to see that all of these terms equal 0, F double prime equals 0 by assumption. So steady would imply Bach flat because all of the terms of our Bach tensor equal to 0. Okay, so we get a couple of nice examples. Going back a few slides to this forwards proof, it's worth noting the backwards proof is slightly more convoluted. It's a little bit more complex, but not much. Really, it's just kind of working back and forth with the matrices here. And you do get a really nice classification, right? I know from this exactly what metrics will work, exactly what things will produce solitons, and using these equations, I was really able to just play around with polynomials and see what broke. Okay, certain things where it would force a metric to be negative and not positive definite, things like that, or wait, polynomials can't do that kind of arguments. So this was actually a really fun string of equalities to work with. And it had a couple of really useful results, as we saw in these two corollaries. Okay. Lastly, I just want to finish up with one sort of actual example so you can see how it works, how finding a soliton would work in this case that is very computational. So I'm going to let these be the components of the metrics of S3, and I'm going to just let it be any left invariant metric on the Lie group SU2. I've used S3 synonymously with this Lie group SU2 because that is what Hellawell used, and I wanted to keep the literature consistent across the board. So do make that note if that note is meaningful to you. Really what it boils down to is using the fact, as Hellawell found, the components of our Bach tensor are given here. Hellawell used a computer to find these, and it was incredibly helpful in my work. Okay. And here, P's and Q's are going to be quartic polynomials. Again, his paper is referenced here if you would like to see them. But using equation 1, that string of equalities that we found, and dividing, say, B11 by G11, B22 by G22, we're able to see that we get two solitons, right? So one is going to be a flat, steady soliton given by G11 equals G22 and G33. And also that string of equalities will also spit out a soliton of the form, or with metric ratios like this. Okay. Really delving into this a little bit more, my polynomials look like this. They were gross polynomials. I'm letting X, Y, and Z represent G11, G22, and G33. But it really was just a matter of looking at how these three specific polynomials interacted with one another to see things like, okay, using a polynomial system, I can look pairwise at each thing and see that when X equals Y, this forces X equal 4Z as well. Or when X equals Z, forces X equal 4Y. Or if none of them are equal, or any two of them really are not equal, then the system has no real solutions. It all came down to playing with polynomial. And from that, let's see, I think it's this one. From that, I was able to get this last result here, get all of these results and start to say, A, I know that there's an expanding soliton. I've found one. And B, I know that any of my other solitons are going to be flat in this case. I've found the only two shrinking ones. I've really classified a lot of these types of solitons. And in so doing, I have found a lot of interesting types of metrics that could be candidates for this sort of best metric group. Okay. But that is all I have. Thank you so much for listening. And please feel free to reach out with questions. I hope to be at a Q&A session later in 2022 to answer any questions that you have. But yeah, if you need to, feel free to reach out via email. Thanks so much.